there is a slightly more complex example of this that we had looked at yesterday. So, let us just go through that also to understand this in a little bit better context. What we looked at yesterday was we have a for loop where I have 6 operations a of I, b, c, d, e and f, right. These have latency of 3 cycles and this has a latency of 12 cycles. Okay. I need to do this some large number of times or maybe even on an infinite basis. As long as data is coming in, I need to do this computation. Okay. Now, what happens in this situation is I actually am dealing with a slightly different scenario than the earlier one. In the earlier case over here, I assumed that read, compute and write could actually happen in parallel and that they could all be executed on different pieces of hardware. Now, I am assuming something slightly different. There is only one processor, but that processor is pipelined. Okay. So, what does it mean to say that the processor is pipelined? It basically means that on every cycle it can initiate a new operation. Okay. So, in principle, even though A takes a latency of 3 cycles, on the very next cycle after starting A, I could start another operation. Okay. So, we already looked at this yesterday and saw that one way of handling it would be, I mean, the normal default would have been A0 2 blanks, B0 2 blanks, C0 11 blanks, D0 E0 and F0. Okay. You could unroll this to get better behavior, which would basically say A0 A1 A2, B0 B1 B2, C0 C1 C2, but I still need to then put in the 9 blanks after that. Then I can do D0 D1 D2, E0 E1 E2, F0 F1 F2, right. Over here what I have is latency equals initiation interval equals 27, and over here what I have is latency equals 27, but II on average equals 9. Why am I saying on average? Because I basically have 3 things being initiated one after the other. That looks like the initiation interval is 1, but I cannot then initiate another A until the entire block has completed, okay, if I want it to be a periodic schedule. So, the effective initiation interval becomes 1. Okay. Now, what is the best possible initiation interval for this? I have 6 operations, right. Therefore, the best possible II is 6. Okay. So, let us now look at, supposing I have a timeline that I put down over here. Right, and I say I want to execute the operations A, B, C, D, E, F, A, B, C, D, E, F and so on. I want to basically get this kind of a pattern going. Right. This should be my block schedule. Right. The problem with this is my dependencies, right. I cannot have A0 and B0 or AI and BI happening one after the other. This is basically not possible, right. There would be a dependency violation over here. But if I take this is fine. What does that mean? It basically means that as long as I had ai over here and bi over here, I will not have a dependency problem. What that means is this should be I minus 1. Okay. Similarly, let us look at what happens over here. This is not permitted, but this would be fine. Okay. Then comes the catch, right? Is this okay? It is not, because I need to have 12 cycle latency after C. So, in other words, after C has started over here, I cannot do anything until 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cycles over here until this point. Okay. So, the only valid thing that I have over here, in other words, is from C I need to go all the way till here. This would be okay, right? That would not be a dependency violation, right? So, in other words, if I had the kth iteration of D over here and the kth iteration of C over here, this is fine. There is no dependency violation, right? What about the rest of them? The D, E, F again have 3. So, as long as I go to the next cycle, I will not have a problem. Okay. Once I have done that analysis, let me put everything together and say, can I use this in order to actually put down the numbers of what is allowed to execute where? Okay. I will just rewrite this quickly over here. Okay. And what I am going to say is, let us say that F I is going to execute over here. Okay. It means that E I must have executed at this point. That is fine, there is no dependency violation. If E I executes here, what will be E at this point? It will be the I plus 1. Okay. If E I plus 1 has to execute over here, this would be D I plus 1, right, and this would therefore be D I plus 2. Okay. Now is where you have to be careful. For D I plus 2 to execute over here, I cannot have the C from the previous iteration, but I can have the D from here, or rather the C from here. This is okay, right, which means that I can then put down that C I plus 2 executes over here. Okay. If C I plus 2 executes here, what this means is this is going to be C I plus 3, this is going to be C I plus 4. Okay. For C I plus 4 to execute over here, B I plus 4 must have executed here, and this would have been I plus 3. Okay. In fact, let us just go back and do the thing there. Yeah. And what we have is, for the dependency on C, if C I plus 4 is to happen over here, yeah, B I plus 4 happens over here, that is fine, and therefore I plus 5 would happen at this place. Okay. Corresponding value of A over here would be I plus 6, this would be I plus 7, and this would be I plus 4. Okay. So, how did I start with this? I essentially drew out a long timeline, put down the pattern that I wanted, and just checked if I want to make sure that there are no dependency violations, what index value should be used for each of the computations. Okay, that is one way of doing it. Did I necessarily need to choose the ABCDEF pattern? Possibly not, but would I have gained anything by changing that pattern? Again, I do not know, possibly not. There may be cases where you would. In this case, actually you would not really gain anything by changing the pattern. Okay. So, all that I have done is I have written out a sequence of computations that would happen, and then put down the index values that would guarantee that there would be no errors. Okay. With that in mind, let us finally look at one block. Sorry, I made a small mistake over here. as far as the A is concerned, this should be I plus 5 because that is what depends on the next B I plus 5. Therefore, this should be I plus 6 over here, and this should be I plus I plus 4 is correct for this one. Okay. So, now look at the blue box, right. This is going to be the loop body, the one that is going to repeatedly execute, which effectively means that now what my for loop looks like is execute A of I plus 6, B of I plus 5, C of I plus 4. Now comes the small jump, D of I plus 2, then we are back to normal, E of I plus 1 and F of I. Okay. And what I will have of course over here is there will be a prologue. What will the prologue consist of? I will have to do everything up to A of I plus 5, or rather up to A of, and after all I is starting from 0, which means that A of 0, A of 1, A of 2, A of 3, A of 4, A of 5 need to be completed outside the loop. A of 0 to 5, B of 0 to 4, C of 0 to 3, D of 0 to 1 and E of 0. All of these will need to get done in the prologue. Okay. And the epilogue would be A has completed. So, in other words, I can only run this until the point that A of I plus 6 is at the end of the loop, right. But what I will then need to finish would basically be B of n, C of n minus 1 to n, D of n minus 3 to n, E of n minus 4 to n, and F of n minus 5 to n. All of these would need to get executed. Okay. As long as I have done that, effectively what happens over here is, this is the loop body which gets an initiation interval of 6. Given the circumstances, given the hardware that I have, that is the best possible initiation interval that I can target, right, because at any given clock cycle I can only initiate one instruction, one function. I have 6 functions to do, therefore, I need at least 6 cycles in order to complete one loop body initiation, right. The penalty that I pay is the prologue and the epilogue, right. Why is it a penalty? Because those are, they are penalty in two ways. One is they are one time costs, I need to actually explicitly write, do them separately. The other is they are extra code, they actually end up increasing the size of your code. So, this is one of those counter examples that I was talking about, right. The general rule for compilation is less code is better. This is an example where less code is not going to be as efficient as writing the extra code including the prologue. Okay. How do you do this in an optimal manner? How do you decide what should be the structure, the index values that you use? Pretty much the way that I have written out over here, but the point is this can be automated, right, because all that the compiler needs to do is find out what are the true dependencies that are there between the instructions, put them all down in a row, and then say okay fine, as long as this runs on the previous iteration there will be no violation of dependencies, and therefore I can get these index values that I need over here. Okay. So, this technique is called software pipelining, because in one way what is happening is it allows you to apply the concept of pipelining, right. The basic idea of pipelining is very clear from this very first picture that we have over here, right. From this picture you can sort of relate why we are thinking of it as pipelining. This is the whole idea of pipelining in hardware, right. You are doing multiple operations, you have multiple hardware units and they can all be kept busy in parallel. Okay. What this technique allows you to do is to apply the same concept to software. Okay. What can of course be done going further from this is to say, let us say that you actually had a code, right, some function where I had multiple sub function calls, right, and let us say that this was being repeatedly called inside a for loop. there are dependencies over here. By doing software pipelining, etc., by changing the index values around and so on, what you could do is, if you think about it, what would actually be happening over here is, the normal execution would be I would take a certain amount of time for A of 0, some other amount of time for B of 0, some other amount of time for C of 0, then followed by again A1, B1, C1 and so on, right. This could then, if I apply the principles of software pipelining, I can change this around and make it A0, B0, C0, right, and A1, B1, C1, A2, B2, C2 and so on. Okay. So, effectively the initiation interval becomes equal to the max of A, B, C latencies rather than the sum of the A, B, C latencies. Okay. This is in fact how you can actually do it in hardware. Okay. So, let us put this into practice. Let us see how this would apply in the context of, yeah. Yes. Correct. Actually, in this case it does not matter, right, because if you really look at what I did over here, even if C had a latency of 13, this would have worked, right, because what is happening is, all that I care about is the dependency, this magenta line that I have drawn over here, which says that this D and this C over here are independent, or rather that is where the dependency is, right. All that I care about is it is sufficiently back in the past so that there is no dependency violation. In other words, Ci is done and guaranteed to be completed before Di needs to start. So, as long as I can push Ci back by sufficient number of iterations, that there is no violation of this constraint, it will work. So, in other words, once I have come up with this schedule, if you look at it, whether the latency of A was 3, 4, 5 or 6 or anything between 0 to 6, this would have worked, right. So, it is not necessary that it is not making use of the fact that they are multiples or anything of the sort. There is no relation between the numbers itself. All that I care about is, once I have put it into a block schedule and then I have that block schedule repeating, I need to ensure that the dependency between the ith iteration of any instruction in a given block has to be satisfied sufficient number of iterations before.